In this video, we are going to talk about the Cauchy Riemann necessary conditions for analytic functions. This is our overview slide, which we'll spend about 5 minutes or less on before we go over each of these three topics in more detail and with more examples. The first thing we'll talk about are the Cauchy Riemann conditions for analytic functions, and these are necessary but not sufficient conditions for analytic functions. That is, if we have a function and we are trying to determine if it's analytic, we can look at the Cauchy Riemann conditions, and if they fail to meet them, we can determine it is not analytic. However, if a function meets the Cauchy Riemann conditions, it has satisfied a necessary condition, but the Cauchy Riemann are not sufficient conditions to be able to conclude it's analytic. So we'll look at that when we talk about necessary versus sufficient conditions. But first, let's just look at the Cauchy Riemann necessary conditions. So suppose we have a function f of z, and we can write that as a real portion of our function plus I times this v of xy, which is the imaginary portion of our function. In other words, v is a real valued function, but it's multiplied by I, giving us the imaginary portion of our function. Then if we suppose f prime exists at a point z naught, then the first order partial derivatives of u and v exists. That's our first statement. And then they also satisfy the Cauchy Riemann equations that the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y, and also the partial derivative of u with respect to y is equal to the negative partial derivative of v with respect to x. And then we can calculate f prime of z as partial of u with respect to x plus I partial of v with respect to x. So for example, if we have f of z equals z squared, which is equal to x squared minus y squared plus 2i xy, then our u function is going to be this x squared minus y squared, and our v function is going to be the 2xy. Then we can show partial of u with respect to x, over here is 2x, and that's also equal to the partial of v with respect to y. Then if we take the partial of u with respect to y, we get minus 2y, which is the negative of the partial of v with respect to x, which is 2y. And so the Cauchy Riemann conditions are satisfied. They're satisfied, but again, that's not sufficient to guarantee that f of z is analytic. And by analytic, we mean the derivatives exist. Next, we will finally get to a sufficient condition for differentiability, or a sufficient condition for analytic functions. So if we have our function f of z written as u plus iv, and we say this function is defined through some epsilon neighborhood of a point z naught. And first, let's suppose that if the first order partial derivatives of the function u of xy and v of xy with respect to x and y exist everywhere in the neighborhood, so the partials exist, and those partials are continuous, that's the second kind of condition, and last, they satisfy the Riemann equations, then we can say that f prime at z naught exists. In other words, it's analytic at this point, and its value then is going to be u partial of u with respect to x plus I partial of v with respect to x. And we will do an example of this. Finally, we have the polar coordinate conditions for Cauchy Riemann. So if our function f of z is written in terms of our polar coordinates or our exponential form, then what we have for Cauchy Riemann is these are the conditions that are met, that r times u times partial with respect to r is equal to partial of v with respect to theta, and u partial with respect to u will equal to minus r times v partial with respect to r. And our derivative, f of z, will be equal to e to the minus I theta u of r plus I vr. And we will see this example later in this video. So that wraps up our overview. So now we can go back and start with the Cauchy Riemann necessary conditions. We'll start by looking at the Cauchy Riemann necessary conditions for analytic functions. So suppose we have a function f of z, which is equal to u of xy plus iv of xy. Then suppose this is our first condition. F prime of z exists at a point z naught. So in other words, the derivative exists at a particular point. Then the things we can conclude are first, that the first, I guess I should put a 1, our conclusions in green, our first order partial derivatives of u and v exist. And then second, we can conclude that those partial derivatives will satisfy the Cauchy Riemann equations here, which is the partial of u with respect to x equals partial of v with respect to y, and partial of u with respect to y equals negative partial of v with respect to x. And then we also have this formula for our derivative at z naught, which is equal to partial of u with respect to x plus I partial of v with respect to x. So it's good to get in an example. So our example is f of z is equal to z squared. We can multiply out our z, which is equal to x plus iy, square it, and we'll get x squared minus y squared plus I 2xy. We want to show that the first order partial derivatives exist everywhere. That's this first statement. And that they satisfy the Cauchy Riemann conditions. That's the second statement. So to show these two things according to this theorem here, what we need to show is that f prime of z, that's our condition over here, exists at some point. And in our last video, when we talked about derivatives, we showed that for f equals z squared, we showed the derivative exists everywhere. And we did that using the definition of our derivative. We showed that the limit is equal to 2z. And I'll leave this for your reference, but again, this was shown in our last video. And the other thing we discussed is that because the definition of derivative here kind of mirrors what the definition of derivative for real valued functions, we find that many of the properties are exactly the same as for real valued functions. So in other words, when we had x squared, the derivative would be take the exponent down in front, you get the 2x, and then you subtract 1, so it'd be 2x. So similarly, you would have the same result if instead of x, you had the complex number z. But here it is proved formally. And now that we know that the derivative exists everywhere, then that means our first order partial derivatives of u and v exist everywhere, and that they satisfy the partials satisfy the Cauchy Riemann conditions. And we can just verify. So u of xy is equal to x squared minus y squared, and v of xy is equal to 2xy. So these exist, they're continuous everywhere. We can take the partial of u with respect to x and get 2x. The partial of u with respect to y, which is over here, is negative 2y. The partial of v with respect to x is 2y. So the negative partial of v with respect to x is negative 2y. And the partial of v with respect to y is 2x. And so you can see that our Cauchy Riemann conditions, u of x equals v of y, and u of y equals negative v of x, are satisfied. This is another problem we had taken the derivative of in the previous video, but we'll rework some of this here. So f of z is equal to the modulus of z, or this absolute value of z, squared. And then from our algebraic properties of complex numbers, which I have here for your reference, the modulus of z squared is equal to z times z complex conjugate. And so you can multiply out your z, which is x plus iy, times your complex conjugate, which is x minus iy, and you'll see it's equal to x squared plus y squared. So u of xy is equal to x squared plus y squared, and v of xy then is equal to 0, since there's nothing multiplied by the imaginary number I. Taking the partial of u with respect to x, we get 2x. Taking the partial of v with respect to y, we get 0. So u of x is equal to v of y. In other words, it satisfies this Cauchy condition only at x equals 0. Over here, when x equals 0. Similarly, looking at partial of u with respect to y, which is 2y, and partial of v with respect to x is still 0, so these two are only equal when y equals 0. So that means f prime of z can only exist at 0, 0. And remember, the fact that here that it satisfies the Cauchy conditions, it's not sufficient to say it's analytic and the derivative exists. But if f prime of z does exist, it's only going to exist at 0, 0. So that's what I mean by can only exist at 0, 0. It's not a guarantee by this theorem here. It does happen, and we did show this in the previous video, that f prime of z does exist at 0, 0. Our next topic is necessary versus sufficient, and then later we'll have this theorem here that gives us sufficient conditions for differentiability. In other words, sufficient conditions to say a function is analytic. Before we go on to the sufficient conditions for an analytic function, I want to talk about necessary versus sufficient, and I'm going to use this example here, which is from a real analysis class or a logic class, which is you can work here only if you have a college degree. And the question I'm going to ask you, is a college degree necessary or sufficient to work here? So the first statement is that the college degree is necessary to work here. It is true that it's a necessary condition. And so if you work here, then I can conclude that you have a college degree. In other words, working here implies you have a college degree, because everyone who works here, they can only work here if they have a college degree. However, a college degree may not be sufficient to work here. That is, it is not sufficient to conclude that if you have a college degree that you can work here. In other words, college degree does not imply that you can work here, because it's possible there are more necessary conditions for you to be able to work here, like having a college degree and being able to write well, or maybe it's speaking French, or maybe it's being able to do differential equations. But the idea is that it's necessary, but may or may not be sufficient. So you cannot conclude from this statement that it will be sufficient. What we have are the Cauchy conditions are necessary for analytic functions, or a derivative of a function. So next what we're going to look at is the sufficient conditions for analytic functions, or differentiability. Analytic means differentiable. So the sufficient conditions for differentiability is, let's say we have a function f of z is equal to u of xy plus I v of xy, and it's defined throughout some epsilon neighborhood of a point z naught. Suppose first that the first order partial derivatives of the functions u of xy and v of xy with respect to x and y exist everywhere in the neighborhood. So that's our first condition. And the second one, these partial derivatives are continuous. That's our second. And kind of our third condition is that they satisfy the Cauchy Riemann equations. U of xy equals v of xy, and u of y is equal to minus v of xy. So it sort of looks like there's two conditions, but there's really three. First, you have the partial derivatives exist, and they're continuous, and finally they satisfy the Cauchy Riemann. Then f prime of z naught exists, and its value is going to be u of x plus I of vx. Our first example is f of z is equal to e to the z, and we want to determine if this function is analytic. The first thing we're going to do, because we're going to use the Cauchy Riemann, we need to separate the z into a real and imaginary part. So we write f of z is equal to e to the z, which is equal to e to the x plus iy, which is equal to e to the x, e to the iy. This part is e to the x, that's real, and e to the iy using Euler is equal to cosine y plus I sine of y. This will allow us to write the real portion is this e to the x times cosine y, and the v of xy is equal to e to the x times sine of y. Now we can take partial derivatives. U with respect to x is just e to the x cosine y. U with respect to y, well, cosine, derivative of cosine is negative sine, so we have minus e to the x sine y. Derivative of v with respect to x is e to the x sine y, and derivative of v with respect to y is e to the x cosine y. So we can see now that our partial derivatives exist and they're continuous everywhere. So the first order partial derivatives also satisfy the Cauchy Riemann equations, because I can look at, where are my Cauchy Riemann equations? They're over here. U of x is equal to v of y. So u of x is equal to v of y, which is true. And then u of y is equal to negative v of x, and that's also true. So again, the three conditions are met. The partial derivatives exist, they're continuous, and they satisfy the Cauchy Riemann equations, and therefore f prime of z exists everywhere, and I can calculate that as u of x, which is e to the x cosine y, plus I v of x, plus I, and my v of x is e to the x sine of y. Our last topic are the polar coordinate form of the Cauchy Riemann conditions, and here are the conditions. Our u of r is equal to v of theta, and u of theta is equal to negative r v of r. And here's our formula for the derivative written in exponential form for our complex number. And I have the polar coordinate form of Cauchy Riemann rewritten here for your reference, and also here x then is going to be a function of u, which is a function of r and theta, which is equal to, since it's x, will be equal to r cosine theta, and y is our v function of r and theta, which is equal to r sine theta. And by Euler, e to the I theta is equal to cosine theta plus I sine theta. So z, which is equal to x plus iy, is equal to r cosine theta plus I r sine theta, which is equal to r e to the I theta. Our first example is to consider f of z equals 1 over z. We want to show the partial derivatives, that they're continuous, that they satisfy the Cauchy Riemann conditions, and then find f prime of z. The first thing we're going to do is write this 1 over z in exponential form in polar coordinates. So f of z is equal to 1 over z, which is 1 over r e to the I theta, which is equal to 1 over r e to the minus I theta, which is equal to 1 over r cosine theta plus I sine theta, using Euler's theorem here. Since we don't want a division by 0 here, we don't want r to be 0, which is equivalent to saying z does not equal to 0. Since r is our radius, theta has to do with our angle. So by saying r is not equal to 0, that's equivalent to saying z is not equal to 0. So next, I can calculate u of r theta. So that will be the real part of this, which is 1 over r cosine theta. Then partial of u with respect to r is, here with respect to r is minus 1 over r squared, and then cosine theta. And then with respect to theta, this just becomes minus 1 over r sine theta. V over r, so that's my 1 over r times my sine theta, and I can calculate v of r is minus 1 over r squared sine theta, and then v of theta is minus 1 over r cosine theta, and I can verify that my partial derivatives satisfy the Cauchy Riemann conditions. In particular, r times ur is equal to, if I multiply this by r, I'm going to get minus 1 over r cosine theta, and that also happens to equal to v of theta, which is my first Cauchy equation. My second one, I'm going to start with minus r vr, which is equal to, where's my vr here? So when I multiply by minus r, I get minus 1 over r sine theta, which is equal to u of theta. And so that's my second Cauchy equation. So since all our partials exist and are continuous when r does not equal to 0 or z is not equal to 0, then f prime of z is equal to, using my formula over here, e to the minus I theta. ur is my minus 1 over r squared cosine theta plus I VR. So VR is here, it's negative, so I'm going to go ahead and say minus I over r squared sine of theta. And again, r does not equal to 0. In other words, this formula is valid as long as z does not equal to 0. For a review, I have two examples for you to try. These are the two problems. The first one is to verify the Cauchy Riemann conditions and find f prime of z for f of z is equal to e to the z. The second problem is to verify the Cauchy Riemann conditions and find f prime of z for f of z is equal to the cube root of r, e to the I theta over 3, where r is greater than 0 and theta is between alpha and alpha plus 2 pi. So pause the video, give the problems a try, and when you come back, I'll have some solutions, and also not just a solution, but a couple of comments for this second problem as well. Here is the solution for the first problem. And the solution for the second problem, which I'll go over briefly. So f of z is equal to the cube root of r, e to the I theta over 3. So I rewrote this cube root of r as r to the 1/3, and I rewrote e to the I theta over 3 using Euler's formula as cosine theta over 3 plus I sine theta over 3. So then I can identify my u of r theta is r to the 1/3 cosine of pi over 3, and my v of r theta is my 1 over r to the 3rd sine of theta over 3. So then I can verify my Cauchy Riemann conditions, which I'll let you check. And since r is greater than 0, the partials all exist and are continuous everywhere. And since I can check my Cauchy Riemann conditions, which I've written here for your reference. So I can look at r u to the r, which will be equal to r times this value here. So I'll get 1/3 r to the 1/3 cosine theta over 3, and I can verify that's equal to v theta. And then my second Riemann condition, u theta should equal to minus r vr. So I have minus r vr, my minus r here, this is my vr, and then I confirm that it's equal to u theta. So the Cauchy Riemann conditions are satisfied. I plug into my formula for the derivative, which is e to the minus I theta, ur plus I vr, and this is what I get here. E to the minus I theta 1/3 r to the minus 2/3 cosine pi theta over 3 plus I 1/3 r to the minus 2/3 sine of theta over 3. So I factor out my common 1/3 r to the minus 2/3 here, and then I multiply my cosine theta over 3 plus I sine theta over 3, which is equal to 1/3 r to the minus 2/3 e to the I theta, and then converting this back to exponential form, e to the I theta over 3. We can actually stop here. This is a fine solution, but I also wanted to do a little more algebraic manipulation to show that the solution is of the form dz z to the 1/3. So if we took the derivative of z to the 1/3, we would get 1/3 z to the 2/3, which if we look at this, the z to the 1/3, that's essentially what this is right here, since we have r to the 1/3 and our e to the I theta is also to the 1/3. So what we're expecting is we'd get something of the form 1/3 z to the 2/3, which is exactly what we have here. We have our 1/3 and then we have our z, so our r then goes to the negative 2/3, and our e to the I theta, when we combine these two, we get also z to the 2/3, or I'm sorry, to the negative 2/3, which is exactly what we would expect. To review what we had covered in this video, we talked about Cauchy Riemann necessary conditions for analytic functions. So we said, suppose we have a function f of z, which is equal to u of xy plus I v of xy, and further suppose that f prime of z exists at a point z naught. then the three things we conclude is the first order partial derivatives of u and v exist, and second, there's only two things we can conclude, and second, the partial derivatives will satisfy the Cauchy Riemann equations here. Finally, we have a formula to find the derivative of f prime, or derivative of f at z, which is partial of u with respect to x plus I partial of v with respect to x, and we worked this example in our video. The next thing we talked about was the difference between necessary and sufficient conditions. Since our Cauchy Riemann conditions are necessary conditions, we also did a theorem to show us sufficient conditions for analytic functions, or sufficient conditions for differentiability. So again, we have our function f of z is equal to u of xy plus I v of xy. It's defined through some epsilon neighborhood of a point z naught. Suppose first, the first order partial derivatives of the function u of x and y and v of xy with respect to x, y exist everywhere in the neighborhood, and those partial derivatives are continuous and they satisfy the Cauchy Riemann equations. Then we know that the derivative exists and we have an analytic function. And we have a formula here for the derivative. We also did examples using this formula. Finally, we looked at the polar coordinate conditions of the Cauchy Riemann, and this is the Cauchy Riemann equations are ur plus v theta, and u theta is equal to minus r vr, and then our formula for the derivative. And we did this example here in our video. So that's it for this video. Thank you for watching.